Today we will discuss some another theorems of modern algebra. So theorem का statement है an order of g is equal to p to the power n where p is prime number, the center of g which is z does not equal to e. इसका प्रूफ देखते हैं. बाय द क्लास इक्वेशन ऑफ ग्रुप वी नो दैट ऑर्डर ऑफ जी इज इक्वल टू ऑर्डर ऑफ जेड प्लस समेशन ऑर्डर ऑफ एन ए इज अ डिवीज़र ऑफ ऑर्डर ऑफ जी. इसको हमने क्वेश्चन नंबर 1 नाम दिया. वेयर द समेशन रन्स ओवर द वन एलिमेंट ए in each conjugate class containing one and more element. Now for all a belongs to G and A, the normalizer A in G is a subgroup of G. By Lagrange theorem, order of Na is a divisor of order of G. Is that order of Na is a divisor of order of G. Also, A does not belongs to Z implies that Na is not equal to G. So order of Na does not equal to order of G, but order of Na is a divisor of order of G is a divisor of order of Na. Order of Na is a divisor of order of G is equal to p to the power n. So order of Na is equal to p to the power n alpha, where n proportional to n. So order of z is equal to uh, small z. Then equation 1 become p to the power n is equal to z, which is equal to summation p to the power n is divisible by p to the power n alpha. So z is equal to p to the power n minus summation p to the power n upon p to the power n alpha. Equation number second. Now p by p to the power n, also p divide each term of summation of the RHS of equation second, because each n alpha is less than n. Thus we see that p is a divisor of RHS of equation second. P is a division of z. E belongs to z, and z is a positive integer divisible by prime p, since z is greater than 1. Hence z must have an element beside e. So z does not equal to e. Therefore p divided by p to the power n does not equal to p divided by p to the power n alpha. So p is divided by summation p to the power n upon p to the power n alpha. So p n minus summation p to the power n upon p n alpha. So p upon z, and z equal to mp, since z is greater than 1. Now there is another theorem. If order of G is equal to p square, implies that order of G is equal to p square, where p is a prime number, then G is abelian. So now we have to show that the center Z of G is equal to G itself. Then obviously G is abelian. Now since G is finite, and so by the Lagrange theorem, order of Z is divisible by order of G, but P by P square or P square by P square, then order of Z is equal to P or P square. If order of Z is equal to P square is equal to order of G, so in this case the order, hence therefore order of Z is equal to order of G implies that Z equal to G. Now if order of Z is equal to P, so P is less than P square, so OZ, order of Z, is less than order of G, then A does not belongs to Z and A belongs to G. If and only if A belongs to G, then NA normalizer of A in G. So G is a subgroup of G. If X belongs to Z, then XA is equal to AX. So X belongs to NA. So Z is a subset of NA. Now A belongs to Na, but A belongs to Z, so Z is a proper subset of Na. So Z is a subset of Na. Order of Na is greater than order of Z, which is equal to P. Since Na is greater than P, by Lagrange theorem, order of Na is a divisor of order of G. So order of Na is a divisor of order of G. So P by P square or P square by P squares, and so order of Na is equal to P or P square. So order of Na is greater than P, or order of Na is equal to P square. So order of Na is equal to P square, which is equal to order of G. Here A belongs to Z by previous theorem, but this is the contradiction from from A does not belongs to Z, then order of Z is equal to P.